small. So if you have the area quite small, then the pressure is quite big and they fall through the ice. Whereas the area of somebody's body lying flat over the ice, that area is going to be much bigger. So if the thing on the bottom of the fraction is much bigger, then the pressure is going to be smaller and the ice will hold. So large area equals small pressure, small area equals big pressure. What is air pressure? Well, the air pressure on something is from all the air molecules bouncing around, hitting the container walls, whatever container we're talking about, putting a force on them. Air always, in fact, any gas wants to move from areas of high pressure to low pressure. So if you blow up a balloon, but don't tie it off, then there's air pressure inside the balloon from all the air molecules bouncing around. If you then let it go, the air inside the balloon, which is at high pressure, wants to end up at the low pressure point, so it scooshes out the back. And Newton's third law says forces come in pairs which are equal in size and opposite in direction. So if there's a force of shooting air out the back, then there's an equal and opposite force forwards which shoots the balloon forwards. But air wants to move from areas of high pressure to low pressure. So, kinetic theory. Kinetic just means movement. So, kinetic theory means movement theory. Movement of what? Well, movement of gas molecules. So, what happens if you've got a box of gas and you've got this box of gas, but in fact it's not a box, it's a flexible walled container. So maybe it's a balloon. A balloon has flexible walls. So what happens if you've got a flexible walled container of gas, maybe air, and the temperature goes up? Well, the air molecules, because they're getting hotter and hotter, they bounce around faster, so they collide with container walls harder and more often. That's the key phrase. When they get hotter, they move around faster, so they collide with the container walls harder and more often. If they collide with the container walls harder and more often, then pressure increases. This pushes the container walls outwards, so the volume increases. What happens if you've got a container of gas and it is a box of gas, so there's hard walls, not flexible wall containers? Well, again, air molecules collide with the container walls harder and more often, so the pressure goes up, and the pressure just keeps going up and up and up. And if it's something like a Lynx deodorant can which you've thrown in the fire, well, in a bonfire, well, the pressure keeps on going up and up and up until the container fails catastrophically, and quite excitingly. But don't do it, kids. What happens if you've got a box of gas and the volume of this box of gas gets bigger? Well, if the volume of this box of gas gets bigger, then air molecules have to move a longer distance before they hit the container walls, which means the air molecules collide with the container walls less often. If they're colliding with the container walls less often, then there's less force on the container walls, so the pressure goes down. Okay? Now, there are 3 experiments which illustrate these principles. So here is a beaker of water, and there's a thermometer, and there's a syringe of air, and as the water is heated and gets hotter and hotter and hotter, because the plunger in the syringe is free to rise up, then you see the plunger in the syringe rise up, showing that the volume is going up and up and up, and you can read off volume values, and you can read off temperature values, and you can see that as the temperature goes up, the volume goes up. Here we've got something with fixed walls. This had like well, part of it was flexible, as the syringe bit going up. Here, none of this container is flexible. It's just like a test tube with a bung at the top, but we have a pressure meter in here. So again, we put this test tube of air in a beaker of water, heat it, the temperature goes up, and the pressure is going up. Why is the pressure going up? Well, because of the story we knew earlier. The air molecules are bouncing inside there faster and faster, so they're hitting the container walls harder and more often, so the pressure goes up. Here we've got a syringe, and we've got a pressure meter attached to it, and if we pull the syringe out, we increase the volume. Here we go, we're increasing the volume, and we'll see that the pressure goes down. Why is this happening? Well, kinetic story tells us that as you increase the volume, the particles of air hit the container walls less often, so the pressure inside there goes down. We're almost there, hang in there. Each of these stories also has a formula or calculation you can do. These you struggle to put in a triangle, to be honest, and they look horrific, but in each case the one subscript means the situation before and the two subscript means the situation after. So in each case you've got a box of gas and something happens to it. You squish it down, or you make the volume bigger, or you heat it up, or you cool it down, and you're trying to find something either before or after. And how do you know which one of these to do? Well, use the shopping list. So if it's giving you pressures and volumes, then you can use the first one. If it's talking about pressures and temperatures, then second one. Volumes and temperatures, the third one. And sometimes if everything is changing, pressures and volumes and temperatures, then you're going to have to use the fourth one. The good thing about these formulas is you don't have to change the units. So if they give you something in kilopascals, then because you've got the same thing on both sides, then the units cancel and you can keep the units the same as they are. Okay. The little thing you've got to remember though is temperatures must be in degrees Kelvin. What is a degree Kelvin? We're almost there. Is this the final? This is the final whiteboard. So what's a degree Kelvin? Well, a degree Kelvin are slightly more logical, really, than Celsius. So the Celsius temperature scale obsesses about the freezing point and melting point of water. So water starts melting and it starts freezing at 0 degrees. So we say, okay, well, how cold can it get? Well, actually, the coldest possible temperature is minus 273 degrees Celsius, because at minus 273 degrees Celsius, the water molecules, which are now a solid, they're in ice, they stop moving completely. Because as a solid, do you remember, molecules, atoms, yes, they're in fixed positions, but they vibrate a bit. But at minus 273 degrees Celsius, all vibration stops completely, and you can't have less vibration than no vibration. And temperature is just a measure of average vibration. Okay, so that's why there's a lowest possible temperature, and the boiling point of water is 100 degrees C. So the whole idea of the Kelvin temperature scale is that somebody just said, well, why not just have the coldest possible temperature being 0 Kelvin, 0 degrees. Now 1 degree Kelvin is the same size as 1 degree Celsius, so therefore it follows that 0 degrees Celsius is 273 Kelvin and 100 degrees Celsius is 373 Kelvin. So do you see what we're doing? To turn degrees Celsius into degrees Kelvin, we add 273, and you need to try and remember to do that before you can use any of these formulas which have temperature in. Anyway, thank you for hanging with me all through this long spiel. It's probably gone on longer than I thought it than what I was aiming for, but hopefully it's been of some use. Okay, all the best, take care, bye for now.